All right, let's peer into a hidden universe, the quantum world. But here's the catch. It only really shows its secrets at temperatures colder than the darkest parts of deep space. So the question is, how do you even build a camera that can see inside a deep freeze like that?
Okay, what you're looking at right here, this is the goal. This is the whole point. It's a microscopic fiber of light being threaded perfectly into a quantum chip. Getting this one connection right is the key to building things like quantum computers and a future quantum internet. The only little problem? It has to happen in one of the coldest places in the entire universe.
So why the crazy cold? Well, think of it like this. The quantum world is unbelievably delicate. Any bit of heat is like a hurricane of noise that just completely scrambles the fragile quantum information. So to make these devices work, you have to get them cold. And I mean really, really cold. The ultimate goal here, the big picture, is to create something called a quantum network. Forget about sending ones and zeros. We're talking about a next-generation internet that transmits pure quantum information. This could unlock technologies that sound like science fiction. Like truly unhackable communication and super powerful distributed quantum computers. And this is the magic number, 10 millikelvin. That's just a tiny, tiny fraction of a degree above absolute zero, the coldest possible temperature. To put that into perspective for you, deep space is about 3 Kelvin. This temperature makes deep space look like a warm summer day. So this gets us right to the heart of the problem. If your quantum chip has to be at 10 millikelvin, how on earth do you build a microscope that can even see it? How are you supposed to align these microscopic parts and check your work when almost all of our technology is designed to work at comfy room temperature? This analogy is it's perfect. It really captures the sheer difficulty of what we're talking about. You're trying to do something with microscopic precision, but your target is locked inside this super complex deep freeze chamber. And to make things even worse, the act of cooling it all down makes everything shrink and shift and vibrate. It's a total engineering nightmare. So, how did people try to do this before? Well, there were basically two big ideas, and neither of them worked out. First, they tried keeping the microscope outside the fridge at room temp and just peeking in through a window. The problem? That window basically acted like a heat lamp, blasting the sample and pretty much cooking it. The second idea was to put the microscope inside the fridge, but all the little moving parts you need for focusing, they just freeze solid, jam up, and break. It was a complete dead end. And this graph, this right here, is the villain of our story. It shows you exactly what happens when the system cools down. Look at the bottom axis. As the temperature plummets from room temperature on the left down to almost absolute zero on the right, those blue dots show how much the focus shifts. Everything inside is shrinking and contracting, which throws the focus off by a whopping 100 microns. That's like trying to photograph something that's constantly moving away from you. So, faced with what seemed like an impossible problem, the researchers had this incredible flash of brilliance. Instead of fighting the cold, what if they just embraced it? They came up with this unbelievably elegant solution. They decided to build a telescope inside a refrigerator. And here it is. This is the design. It's ingenious. Just take a look. You can see the sample and the main objective lens way down at the bottom, in the absolute coldest part of the whole machine. But the really clever part is how the image, that red light path, gets beamed all the way up through warmer and warmer stages and right out the very top. And here is the absolute genius of it all. The researchers figured out the single biggest reason things were failing: moving parts. In that extreme cold, they just break. So their core idea was beautifully simple: get rid of them. The sample and the main lens are bolted down, totally fixed in place. No moving parts means, well, no breaking parts. So if nothing inside moves, how in the world do you focus the image? That's the trick. This series of lenses you see here, they act like a really sophisticated periscope. They grab the image from the very bottom, pass it up through the system, and perfectly recreate it outside the fridge. All the delicate focusing stuff can be done at room temperature using standard, reliable equipment. It's just brilliant. Now look, a clever design on a piece of paper is one thing, but the real question is always, does it actually work? Can this telescope in a fridge really deliver a clear picture from the abyss of absolute zero? Well, the proof, as they say, is in the pictures. And here is the very first test. On the left, you've got a standard resolution chart imaged at normal room temperature. On the right, that is the exact same chart, but this time it's been cooled down to a frigid 70 millikelvin. Just look at that. Even in that deep freeze, the image is still incredibly sharp. You can make out even the finest little lines, clear as day. And here's the hard data. You could call it the microscope's final report card. This graph is all about resolution. The blue line, that's the performance at room temperature. That's our ideal. The red line is the performance way down in the deep freeze. And yeah, there's a little drop, but what's absolutely crucial here is that the red line is stable. Once it gets cold, that image quality stays rock solid.
So what does that rock-solid performance actually mean? It means a final resolution of 1.1 micrometers. Now that number might not sound like a lot, but in the world of quantum engineering, it is a huge deal. It's more than sharp enough to clearly see and manipulate the tiny little structures on their quantum chips.
And here it is, the payoff, the hero shot. This is a real image taken at the base temperature of 10 millikelvin. You see those tiny vertical lines? Those are the quantum waveguides on a diamond chip. This crystal clear image is the ultimate proof that this incredible telescope in a fridge actually works perfectly.
So, what does this all really mean? Why is having a really good camera inside a really cold fridge such a big deal? Well, because this isn't just about taking a nice picture. It's about unlocking the entire future of quantum technology.
And that brings us right back to where we started. With this new clear eye into the deep freeze, scientists can finally do these mind-bogglingly delicate tasks, like perfectly aligning this optical fiber that are absolutely necessary to build and test the next generation of quantum devices. It literally turns what was an impossible engineering feat into a routine procedure.
You know, you could argue this breakthrough is as important as when the first microscope was invented for biology. It doesn't just solve one little problem, it opens up an entire unexplored world for us to play in. Which leaves us with one really tantalizing question. Now that we can finally see what we're doing in the quantum realm, what incredible things are we going to build there?